Good morning, students. Today I'll be explaining, starting with the comparison of RC phase shift oscillator and Wien bridge oscillator that we have already studied. In the RC phase shift oscillator, the feedback network consists of three RC sections. As we have seen in the RC phase shift oscillator, there are three RC sections or three RC networks in the feedback network. In the Wien bridge oscillator, the feedback network is a combination of high pass and low pass network. If we consider the Wien bridge oscillator here, so this is the Wien bridge oscillator, right? In this Wien bridge oscillator, the feedback network consists of two RC sections. So this RC section is called as the high pass section. It passes the higher frequencies, right? And this section is called as the low pass section or the low pass network. So the second RC network in that is parallel combination, which passes the low frequencies. Okay, so this series combination of R and C passes the higher frequencies, right? Higher frequencies, and this R and C2 parallel combination, this is passing the lower frequency. So it's a combination of high pass and low pass filters. Okay, it passes high frequencies means it blocks the lower frequencies, and this R2 C2 parallel combination passes lower frequencies means it blocks the higher frequencies. Then the frequency of oscillation of the RC phase shift oscillator is given by F is equal to 1 upon 2 pi RC root 6 plus 4K. The frequency of oscillation for Wien bridge oscillator is given by F is equal to 1 upon 2 pi RC. The condition for sustained oscillations of RC phase shift oscillator is A is greater than or equal to 29, whereas for the Wien bridge oscillator it is A is greater than or equal to 3. The variable frequency operation is obtained by varying all the three capacitor values simultaneously in the RC phase shift oscillator, whereas in the Wien bridge oscillator the frequency can be varied by varying two capacitor values because it consists of only two RC sections, one series RC section and one parallel RC section. So the frequency can be varied by varying the capacitor values in the two RC sections in the feedback network simultaneously. RC phase shift oscillator is used for low frequency range. The Wien bridge oscillator is also used for low frequency ranges. Here in RC phase shift oscillator, there is a feedback phase shift of 180 degrees. In the feedback network, there is a phase shift of 180 degrees. But here in the Wien bridge oscillator, there is no phase shift of the feedback network. And in the RC phase shift oscillator, the amplifier circuit, there is 180 degree phase shift, whereas in the Wien bridge oscillator, in the amplifier circuit, there is no phase shift. So in the Wien bridge oscillator, here if we consider this circuit in the Wien bridge oscillator here, right, it is a series combination of RC and a parallel combination of RC. So when this R1 is made equal to R2 and C1 is made equal to C2, at one particular frequency the maximum voltage is obtained. That is called as the resonant frequency. At one particular value of the input frequency, the maximum output voltage is obtained, and that is called as the resonant frequency. Okay, so at the resonant frequency, the capacitive reactance of the circuit Xc will be equal to the resistance of the network or the resistance of the entire circuit, that is R. So Xc will be equal to R under the resonant condition, that is at a particular value of input signal frequency, the output voltage is maximum. So at a particular frequency, the output voltage is maximum. That condition is called as the resonant condition. Okay, so at the resonant condition, there is no phase difference between the input and the output. So the phase shift or the phase difference between input and output is 0 degrees. Okay, and hence we are saying that in the Wien bridge oscillator, the feedback network, there is no phase shift, and also the amplifier circuit, there is no phase shift in the Wien bridge oscillator circuit. So these are the differences between RC phase shift oscillator and Wien bridge oscillator. In the examination, the question can be explain the comparison between RC phase shift oscillator and Wien bridge oscillator, or write the comparison between RC phase shift oscillator and the Wien bridge oscillator. So you have to draw this table, make two columns, RC phase shift oscillator and Wien bridge oscillator, and write the differences between the two. Let us solve an example on RC phase shift oscillator. Find the values of RC, R dash and C for RC phase shift oscillator for a frequency of oscillation of 1000 Hz. F is given, frequency is 1000 Hz. A transistor with HFE is equal to 200. Beta is given or HFE is given, it is 200 current gain, and HIE is equal to 2 kilo ohms is available. HIE value is 2 kilo ohms. Okay, that is the input impedance. The input impedance of the circuit HIE is equal to 2 kilo ohm. So we know that if you want to select R and R dash, the relation is R is equal to R dash plus HIE. R is equal to R dash plus HIE. If we look into the circuit of the RC phase shift oscillator here, right, RC phase shift oscillator, the input impedance is given by R dash plus HIE, the input resistance of the circuit. The total input impedance or the total input resistance of the circuit is this resistance R dash plus the input impedance of the RC coupled amplifier, that is common emitter RC coupled amplifier, that is HIE. Okay, so this total R dash plus HIE, that gives the total input resistance of the entire RC phase shift oscillator, and hence it is written here that in the solution is written here that R is equal to R dash plus HIE, or R dash is R minus HIE. If you want R dash to be positive, then R should be greater than HIE. Is it not, students? If you want R dash to be positive, then R should be greater than HIE. So that is R is greater than HIE. HIE is given here, it is 2 kilo ohms. So R must be greater than 2 kilo ohms. So the nominal value of R that we can choose is 2.7 kilo ohms. 2.7 kilo ohms, right? So if we choose R is equal to 2.7 kilo ohm, we are choosing here the value of R. So R dash will be R minus R dash will be R minus HI. R we are taking it as 2.7 kilo ohm. We are using the approximate value of R, that is 2.7 kilo ohm, minus HIE, that is minus 2 kilo ohm. So R dash will be 2.7 kilo ohm minus 2 kilo ohm, that will be 700 ohms. Then we have to select the value of RC. We know that the condition of the sustained oscillations for the RC phase shift oscillator is HF is greater than 4K plus 23 plus 29 by K. This is a condition to get the sustained oscillations or the stable oscillations of the RC phase shift oscillator. HF is how much they have given? It is 200. HF is 200. 200 is greater than 4K plus 23 plus 29 by K. Now here we can choose the value of K according to our will and wish. We are free to choose the value of K to meet the above requirement. So if we choose K is equal to 1, let us see what will happen. If we choose K is equal to 1, so 200 will be greater than 4 into 1 plus 23 plus 29 by 1. So that is 200 is greater than 4 plus 23 plus 29. So it will be 200 greater than 56. The condition is satisfied. That is HFE will be greater than 4K plus 29 will be greater than 4K plus 23 plus 29 by K. This 200 greater than 56. So K is equal to 1 satisfies the condition for sustained oscillations, that is Barkhausen criteria. So K is equal to RC by R. In the derivation of the frequency of oscillation for the RC phase shift oscillator, we have assumed K is equal to RC by R. You can see here for the RC phase shift oscillator, we have assumed K is equal to RC by R here. K is equal to RC by R, right? So if we take K is equal to RC by R, then we will be getting RC is equal to K into R. K we have taken it as 1. 1 into R. R we have assumed as 2.7 kilo ohms. That comes out to 2.7 kilo ohms. Now the frequency of oscillation of the RC phase shift oscillator. What is the frequency of oscillator? That is the frequency of transistor RC phase shift oscillator given by transistor RC phase shift oscillator frequency equation is given by F is equal to 1 upon 2 pi RC root 6 plus 4K. F is equal to 1 upon 2 pi RC root 6 plus 4K, or C is equal to 1 upon 2 pi RF root 6 plus 4K. So the equation for the capacitance will be equal to 1 upon 2 pi RF root 6 plus 4K. That is 1 divided by 2 pi. R is 2.7 into 10 raised to 3 into F is 1000. They have given frequency value as 1000 hertz. Substitute that, fine. Root of 6 plus 4 into 1, K is 1. So if we calculate this, it comes out to 18.6 nanofarad. Fine, students. So like this, we have to solve this particular example. Let us move on to a second example. The frequency selective circuit arms of Wien-Bridge oscillator uses C1 is equal to C2 is equal to 0.001 microfarad, R1 equal to 10 kilo ohm, while R2 is kept variable. The frequency is varied from 10 kilohertz to 50 kilohertz. By varying R2, find the range of R2, or they can also ask in this way, find the maximum and minimum value of R2. Both are one and the same. Okay. Here read the question first. The frequency selective circuit arms of Wien-Bridge oscillator. So in the Wien-Bridge oscillator, they use the values C1 is equal to C2 is equal to 0.001 microfarad, R1 equal to 10 kilo ohms. Okay, R2 is variable. The value of R2 is variable. So we have to vary the frequency from 10 kilohertz to 50 kilohertz by changing the value of R2 or by varying the value of R2. Then they are asking to find the value of R2 maximum and R2 minimum, or find the range of R2, or find the maximum and minimum value of R2. We know the frequency of oscillator equation for the that is Wien-Bridge oscillator, that is F is equal to 1 upon 2 pi square root of R1 R2 C1 C2. Okay, this is the frequency of Wien-Bridge oscillator equation. So first one, for F is equal to 10 kilohertz, they are given first value of frequency as 10 kilohertz. So for F is equal to 10 kilohertz, if we substitute, and that is 10 into 10 raised to 3 is equal to 1 divided by 2 pi square root of R1 is 10 kilo ohms, 10 into 10 raised to 3 into R2 into C1 into C2. So C1 into C2 both are one and the same, it is 0.001 microfarad. So C1 into C2 will be C1 square or C2 square or C square, that is 0.001 into 10 raised to minus 6 the whole square. So if we simplify this, then the answer will be R2 is equal to 25.33 kilo ohms, the value of R2. Fine. Similarly, for the second frequency, that is F is equal to 50 kilohertz. If you substitute F is equal to 50 kilohertz in the basic equation, okay, F is equal to 1 upon 2 pi square root of R1 R2 C1 C2, then we get 50 kilohertz, that is F 50 into 10 raised to 3 is equal to 100 by 2 pi into square root of the value of here, that is R1 is 10 kilo ohms, that is 10 into 10 raised to 3 into R2. We are supposed to find the value of R2. This into 0.001 microfarad, that is 0.001 into 10 raised to minus 6 the whole square. It is C1 into C2 or C square or C1 square or C2 square. So if we simplify this, then the value of R2 that we'll be getting is 1.013 kilo ohms. Fine, students. So here we have found out the value of minimum value of R2. Minimum value of R2 is 1.013 kilo ohms, and the maximum value of R2 is 25.33 kilo ohms. So what is the range of R2, students? Range of R2 is between 1.013 kilo ohms to 25.33 kilo ohms. Right? It is 25.33 kilo ohms is the maximum value of R2, and minimum value of R2 is 1.013 kilo ohms. Hence we say that the range of R2 is between 1.013 kilo ohms to 25.33 kilo ohms. So we are supposed to solve this particular example in this way. Next is LC oscillators or tuned oscillators. LC oscillators are also called as tuned oscillators. So as the name goes, LC oscillator. So this LC oscillator uses LC circuit, that is combination of inductance and capacitance in the feedback path, okay, to generate the sinusoidal oscillations. So parallel LC circuit is also called tuned circuit or resonant circuit. There are various names for LC oscillator. It is called as tuned oscillator also and a resonant circuit also. The frequency of oscillation is determined from the resonant condition of the tuned circuit. The resonant condition is at one particular frequency, the output voltage is maximum. So this condition is called as the resonance condition. That is, the frequency is tuned to a particular value such that at that particular frequency the output voltage is maximum. This condition is called as the resonant condition. So these oscillators exhibit high quality factor. So when there is quality factor high, then the distortion will be less and the stability will be high, resulting in good frequency stability. These LC oscillators or tuned oscillators are used to generate the frequency in the range of 100 kHz to 100 MHz. So the basic configuration of LC oscillator is shown here. This is the basic configuration of LC oscillator. Depending on the value of this is the amplifier, and this is the feedback path, which consists of the parallel combination of X1, X2, and X3, and hence it is called as parallel LC oscillator circuit. Right? Depending on the values of this X1, X2, and X3 compound, nature of this X1, X2, and X3, you have two types of oscillators here. If X1 and X2 are capacitors and X3 is inductor. If X1, X2 are capacitors and this X3 is inductor, right, then it is called as Colpitt's oscillator. The circuit is called as the Colpitt's oscillator. And if X1, X2 are inductances and X3 is capacitance, if X1, X2 are L, that is inductance, and then it is called as Hartley oscillator. It is called as Hartley oscillator. Okay. So like this, the LC oscillators or the tuned oscillators or the resonant circuits are classified as Colpitt's oscillator if x1, x2 is capacitance and x3 is inductance. And if x1, x2 are inductance and x3 is capacitance, then it is called as the Hartley oscillators. Amplifier can be a FET amplifier, that is a field effect transistor can be used as an amplifier. A transistor can be used as an amplifier, that is a BJT, or an operational amplifier can also be used as an amplifier. So this amplifier can be an FET, or it can be a BJT transistor, or it can be a FET, it can be a BJT, or it can be an operational amplifier. Right? These are the various types of that is components can be used as an amplifier, that is a transistor or a field effect transistor, FET, or an operational amplifier, op amp. In short, it is called as op amp or the operational amplifier. Fine, students. In today's class, students, we have covered with the comparison between RC phase shift oscillator and Wien bridge oscillator. Then we have solved two examples, one example on RC phase shift oscillator, another example on the Wien bridge oscillator, right? And then we have started with the introduction to LC oscillators or tuned oscillators or resonant circuit. And based on the x1, x2, and x3 values, the LC oscillators or tuned oscillators are classified as Colpitt's oscillator and the Hartley oscillator. Okay. Hope everybody have understood here. If there are any questions on today's class, send your questions to me. I will answer to your questions. Thank you.